Okay, picking up from this morning, I've now restarted the computer, reorientated the notebook, the background thing, and we appear to be getting it to work now. So I've just gone through and I've just filled in the key points off those sheets that we looked at this morning. So although I've talked through it, I've now added on to here 3 and 4 from the first sheet, so the mechanism and the will the reaction work. So those of you who are here at the moment, obviously you've seen it in front of you anyway. And then the other sheet that we looked at, the reactive sites and organic reagents sheet. And then where this leads us to, the fourth point on there, reaction mechanisms, is now what we're going to have a look at in a bit more detail. My aim is to try and get this done fairly quickly. Sorry, I've put an extra sheet of diagrams in because I know that's where I'm heading for. It'll make life a bit easier. The first thing we need to do is to sort of get an idea about how these curly arrows work. So you've now got a sheet that's headed up drawing mechanisms. It then gets a bit more complicated, but once you're sort of equipped with the basics as to how to draw these things, then actually the assignment is not that difficult. It does obviously sort of rely on you explaining thoroughly what's happened, not just copying some stuff out, and then taking the processes as far as you can, maybe. But this idea about drawing the mechanisms, the key thing is where we ended up with that last bit, which is the fact that you have to identify 3 specific parts, and that's in the box down at the bottom of this sheet, and you need to be showing how electrons are moving. So the top box on here then, about electron rearrangements and curly arrows. So electron rearrangements and curly arrows then is the sort of key, because this is what a reaction is. So the idea of curly arrows, and that is what they're called, they don't have any... What happened there? They don't have any other magical sort of description. It's funny, isn't it? You know, in all of science you get these sort of great big words that describe this, that and the other, and then come to this and they're just called curly arrows. And yeah, sometimes it's like that. This idea of breaking bonds and making bonds then is to do with taking electrons from one place, putting them somewhere else. So taking them away breaks a bond, putting them somewhere else will usually make a bond. You might be just transferring charge maybe, but you've got 3 different locations for electrons that we're going to be moving about. All right, so if you have a look on your sheet there, we've got the electrons will be one of these 3 places. We've got the sigma pairs, a sigma bond, which is your single bond. You've then got the pi pairs, which are the additional ones. They're in addition to the sigma pair. And then you've got lone pairs as well. Those are ones that are not involved in bonds. So those can be shown as, with a little sort of ring round them, but it depends whether that's a useful thing to do. So to start with, you've got the electron arrangements, you've got 3 locations. So you've got a sigma pair, you've got pi pairs, or you've got lone pair. Right. Sometimes we're also going to have single lone electrons as well, which are another story altogether. The rearrangements that you've got, possibly, you've got listed there possible 3 options that you can go from a sigma pair changing into a lone pair. So that's a pair that's been in a bond between 2 atoms, becoming a pair on a single atom. So you've got a pair there moving from a bond which attaches a hydrogen to a chlorine, becoming both attached to the chlorine. Now, that leaves the chlorine with an extra electron compared with its stable atomic form, where you'd have 7 on the outside. That's it's giving it 8, so it's actually a chloride ion. So in that case, we've got hydrogen chloride being broken to give a chloride ion, and we're not told what happens to the hydrogen, but that's irrelevant at the moment. All right, so you can have your options in a reaction from these. You could have sigma to lone pair. All right, I'm keeping it simple because you've got it on the sheet anyway. The second option, you can have a pi pair changing into a lone pair. So from a double bond, you could have that additional pair being moved onto an atom on, attached by the bond. Again, with this one, you can see what we've ended up with is an oxygen that's actually got an additional electron. So we've got a negative ion there. So we can have, what's that, pi pair to a lone pair. And then you could have a lone pair changing into a pi pair. So that's pretty much that last one, but in reverse, isn't it? Similar sort of setup. So you could have lone into pi. All right. We don't, possibly there are other options as well, but we don't want to get too deeply into this. This is only one small part of what we're doing. You've got an example in the middle left box there, a simple acid-base reaction. It doesn't look like an acid-base reaction to you, I'm sure. This is water and hydrochloric acid. Well, actually it's not. It's water and hydrogen chloride. And this is how we would make hydrochloric acid. But the reaction, when you put hydrogen chloride into water, we describe the hydrogen chloride as ionizing. We say it ionizes so that you get hydrogen ions. In fact, that's a bit of a lie. And chloride ions. But in fact, what you get are not just hydrogen ions on their own, but H3O plus. All right, the hydrogen actually attaches itself to the water, and you get an overall charge on that, and chloride ions. But it tells you there that the new bond occurs between the oxygen of the water molecule and the hydrogen atom that came off the hydrogen chloride. You've got to break that off first, of course. But if you were showing that using curly arrows, you've got, I don't want to use this one too much because it's not an organic example, but the curly arrows are showing you where those electrons go. And it's very precise. The blunt end of the curly tail on the arrow starts at the pair that are moving. The pointed end of the arrow ends by the atom that it's going to. Right? So you've got to be quite precise with these curly arrows, and it is showing you, where the electrons end up on that. I want to move on from that one because it's not really relevant to what we're doing. Over on the right-hand side, you've got fish hooks and free radicals. So hang on, let's just, for the sake of the recording on this, I'll put this in in brackets. 2 is the acid-base example. All right, not one that we're pursuing, but just there to start illustrating where the electrons are going. The third box there, fish hooks and free radicals. This one is worth a look. Okay, now so far we've not met any of the fish hooks, but up in that top box, the electron rearrangements and curly arrows box, you've got whole curly arrows. Now those whole curly arrows are showing you the movement of whole pairs of electrons. The other option is for single electrons to move. And I'm going to draw out the diagram there in a little bit more detail because it's a bit squashed. But when you have a half arrow just showing the movement of single electrons, that's what they call a fishhook. All right, so that a whole arrow is movement of an electron pair, whereas that with a single bit to it, I don't know if it matters which way you do it, that's movement of a single electron. So the example that they've got there is with chlorine, and this is a useful one to do because what is created in this particular example is something called a free radical. Now, free radicals, they sort of popped into everyday use many years ago now, and they were always described as sort of bad things in your body and that sort of thing, and we had to mop up the free radicals and all this sort of thing. Free radicals are potentially quite dangerous, the reason being they're very, very reactive. And the reason they're very, very reactive is that they have single unpaired electrons. Now, if you've got a single unpaired electron, then it's just asking to react with something else, either get rid of it or to pair it up or, remove it in some way. And free radicals have these odd unpaired electrons. So the example that you've got there is an example which is the splitting of a chlorine molecule into what are effectively two chlorine atoms. All right, now, if you write that like that, you're not really describing what's happening. But we know that chlorine doesn't exist as atoms. And the reason it doesn't exist as atoms is it's got 7 electrons in its outer shell. So it's very, very reactive. It's, it's nearly full. And so chlorine hangs around as biatomic, 2 atoms stuck together in the molecule Cl2. And the way that we would do this to draw it, you've got it on the sheet, but like I say, it's a little bit cramped. So we've got, I'm going to draw them a bit bigger and clearer and do them in 2 colours instead of the way they've got them there. All right, now these are identical chlorine atoms. The one on this side, I'm not going to do them as dots and crosses, we'll just do them all as dots because I've got them in the different colours. Right, here's one of our chlorines with, let's get it the same way around as this. There's its 7 electrons. All right, so I'm doing it Lewis structure style. And the other one, all right, there's our perfectly happy chlorine molecule. 2 atoms bonded together covalently, sharing an electron with each other so that they've each got the full complement of 8 in their outer shell, nice and stable. However, there are situations where this can be broken, and from this bond in the middle, the red one can attach itself to the right-hand chlorine, the black one can attach itself solely to the left-hand chlorine, which you're thinking, well, that's where they belong anyway. But in this bond, they're actually being shared. So the process would be described, and you can see the arrows, can't you, just about on there, that you've got this one, the red one, being given to that chlorine, the black one being given to that chlorine, and that's where the fishhooks come in. And you get this split, which they've sort of done with a bit of a zigzag line. I'm not sure if I can make that work quite the same way, but like that. That's the split between the 2 of them. And so what you end up with, that's our original, then it's not too much of a challenge to see that what you're going to end up with from that is, well, none of them is like this, and the other one is like that. I've managed to put those in the same place. Now, when you look at that, you think, well, yeah, right, that's a chlorine atom. Now, the pairs of electrons, so, you know, this pair, this pair, this pair, fairly stable. This pair, this pair. Remember when we were filling up the orbits, yeah? Sorry, orbitals. But we've got this one and this one, all right? So these are unpaired electrons. And so these are described as chlorine-free radicals. All right, they're not just chlorine atoms, they're free radicals. They've been released from a chlorine molecule. Now, the thing about a free radical is how do you write it? And it's actually quite tricky, and I'm not sure that there is a way in Word. But what you would have is what we had up at the top there, where I had Cl2 being broken up into two atoms. We should represent that as free radicals rather than atoms, and it's usually drawn with a dot. Now the dot should really just go next to it. And it's quite a difficult thing to... Yeah, there are ways, I think, but that dot represents the unpaired electron. All right, so these are free radicals, which are essentially the same as atoms. It's just you don't ever get atoms of chlorine in reality, but you know, we wouldn't say that we actually break a chlorine molecule into two atoms of chlorine. We say we break it into two free radicals. Now, you can get these free radicals in all sorts of places, and the first thing we're going to look at, the first of the mechanisms, the free radical substitution, involves chlorine radicals, methyl radicals, and something else I think in there as well. Can't remember at the moment. My brain's not up to that yet. All right, so what distinguishes this particular example, I should add, is the fact that we've split this completely evenly. So we've ended up with two identical halves, if you like. The splitting process is called fission. That's just a general word for splitting. And because it's an equal split between two identical particles, we call it homolytic. All right, so homo meaning the same, lytic meaning splitting, and then fission also meaning splitting. This is homolytic fission. Hydrolysis involves water, yeah? And is actually more complicated than we give it credit for. All right, but this is just introducing the blue arrows up there being the movement of those single electrons. The process here producing two chlorine radicals. The unpaired electrons being particularly reactive, and yeah, this is how we are supposed to draw them, but yeah, be a bit tricky. Right, so that I've got all that out of that one little box. That means I've probably overlapped into some of the other stuff as well, but that's not a problem. So the other bit then that's important to us is that box at the bottom about how to draw the mechanisms. And this is the 3 steps that we met briefly this morning. So let's elaborate a little bit on those. When you draw it, you must make sure that you have these 3 steps. Sometimes you might need something else as well. That's not 3, is it? That's 4. fission was the 3, so that's 4. 3 steps here. Essentially, it's before, during, and after. You know, just sort of showing where the atoms are, what's bonded to what, where the electrons are, where they've moved. So you need to make sure you have lined your particles up, those steps. So you have before reaction, with the reactants correctly aligned so that they will react. Don't just stick them anywhere. Although the chances are you're going to be using images of these anyway, you're not going to be trying them yourselves. So this is probably not too critical. The second step is during the reaction, and it depends what it is as to how much detail you're going to have to put in there, showing the electron movements with the curly arrows, whether they're full ones or fishhooks. And then it's after the reaction, so you must, you know, it's just making sure you've got all this. So this would, well, products is what we get here. Okay. Now, I realise that I've not necessarily put the sheets in the right order for what we need next. I've given you, I think there's 2, 3 more slides on examples I'm going to come back to in a minute. There's what I should have put in at this point was the couple of slides from Chem Guide on using curly arrows in reaction mechanisms, because that is, you know, Jim Clark's wonderful description of how to use the curly arrows and the fishhooks, and it is just, you know, very, very straightforward. I'm not going to read through that. You're perfectly capable of reading. The examples that we met earlier, we have this idea of classifying organic reactions as nucleophilic or electrophilic, and on top of that you could then have addition, elimination, substitution. The following sheets, and this is, we are not really going to spend any time looking at these, give you some examples of these. So you've got, let's have a quick look. We've got homolytic substitution, homolytic addition, heterolytic electrophilic substitution, heterolytic electrophilic addition. So there's a bit of a variety there. That doesn't sort of necessarily cover everything that we were talking about earlier, but the very first one of those, homolytic substitution, the free radical photochemical chain reaction. That's the first one that you want. So if you want to just put a mark by the side of that one. If you have just a quick skim through it, this starts off with a chlorine molecule being broken into 2 chlorine-free radicals. You've then got some sort of chain reaction in the middle. Yeah. And then stage 3 is what they call a termination reaction, but it's not quite adequate for what I want, that one. The second one on there, homolytic addition, that's a polymerization reaction. We aren't going down that route, so we don't need that one. Heterolytic electrophilic substitution, the nitration of benzene, we don't need. And then heterolytic electrophilic addition, we do need. All right, so you need the first one and the fourth one. The electrophilic addition is alkenes with halogens, that's chlorine, bromine, fluorine, any of those, and hydrogen halides, so that could be hydrogen chloride, hydrogen bromide, hydrogen fluoride, any of those. All right. And then the sheet that follows is literally just there to scare the heck out of anybody who thinks they want to do a chemistry degree. I wouldn't have a clue where to start on that these days. I never have learned all of that, but it's if you study biochemistry or anything like that, then a lot of these things are really quite important. They're very important in manufacturing processes as well. Right, what I do want to do, however, is concentrate on the two examples that come up in the assignment, and I'm trying to remember what I've actually given you. There it is. Right, I've given you, hang on, let's get myself up with another page so I can make a mess of this. Okay, so for the assignment you have part B, 1, is methane and bromine. And part 2 is ethene and hydrogen bromide. And these two reactions are the examples I was just talking to you about. We've got free radical substitution, so we're going to have a quick look at that. Not in too much detail because otherwise I'm literally just doing it for you. And it is straightforward once you get the hang of it. And then the other one, electrophilic addition. So, these are the ones you've got to produce illustrated explanations for. It says, explain in detail using curly arrow diagrams to illustrate electron movements, the mechanisms involved in the reactions between. You will find on ChemGuide the one I'm going to go through, methane and chlorine, but you will also find the bromine one. All right. And I think you'll find the hydrogen bromide or chloride one on there as well. But there are lots of other sources, I should say, other websites are available. The first one, free radical substitution. We have, I'm going to go on to my next sheet. I've put a couple of diagrams, I just copied and pasted off the internet to show some of the sorts of diagrams you'll come across with this, and I'll talk you through. But basically, the free radical substitution you've got 3 steps to look at. Not necessarily substitution. Substitution. I couldn't convince myself there were 3 T's in that. The first thing you have to get, this has to be initiated. So there's initiation, and this involves ultraviolet light. Okay, this is a reaction that can be started by a flash of UV light. And the UV light is responsible for the homolytic fission of the chlorine, the Cl2, into chlorine radicals. And that's what will start this off. Once you've got chlorine radicals, then the whole lot gets going. All right, so once you've got those, everything else follows on from that. You have then propagation. Now, the propagation part of it is once you've produced chlorine radicals, as long as there's enough of them and enough methane to react with. This will actually just keep going, keep going, keep going, to be honest, until you run out of something. But this is a chain reaction, which I'll show you in a minute, where the chlorine radical reacts with methane, and it sort of carries on, carries on, carries on, until something needs to bring it to a close, and you get termination. And you get your final products, you know, the whole thing comes to a stop. Right, I'm going to move the diagrams from the next slide, so just bear with me. Just make yourself some space for it. Now, this one, it's always tempting, you know, you have a look around and you find, oh, that looks nice. I tried to find one that was missing a bit. And this is what happens. All right, I'll take you through the main parts of this. No curly arrows in this. They're not compulsory in this particular example, but they do help. Here is an example of the sort of reaction descriptions you can have. The ultraviolet light is responsible for breaking the chlorine molecule, the Cl2 here, into two chlorine radicals. Now that's with the dot higher up. I think that might be better than the way I was drawing it just by the side. And that's the initiation. So once you've got these highly reactive chlorine radicals, or bromine radicals, as you will find for your assignment, that is what triggers everything else. It's that is like you poking a domino in a whole line of them. Something's got to get it started, and it's this production of the chlorine radicals that gets the whole thing started. You then have these propagation steps, and what happens is a chlorine radical will react with some methane. All right, so that's what we've got here. So here are our chlorine radicals that have been produced to start with. Here's our chlorine radical again. So it's one of those. All right, it doesn't matter which one. Let's say it's that one. Reacts with the methane here, and that reactive particle there takes the place, essentially, of one of the hydrogen atoms in the methane. This is why it's called substitution. Right? And what happens to achieve that is, and we're not seeing electrons moving here, so it's not clear on this, so this is not the ideal sort of diagram. What we get is one of the hydrogens is lost from the CH4, the methane, and attaches itself to the chlorine, so there. And that leaves our methyl group, this thing here, is a methyl radical. All right. Now, the problem with that is very often, where do you put the dot? And you will see it put after the CH3. It is more accurate, if you think about it, to put it next to the C, because that's where the unpaired electron's going to be. So it's better to have it there, but if you put CH3 dot, it's not too much of a problem. So we've created another free radical in all of this. So, all right, well, that means we've still got something reactive about. So the methyl radical reacts with more of the chlorine that we had at the beginning. All right, so that is just more chlorine. It picks up a chlorine atom from the chlorine up there and leaves a chlorine radical behind. And so we've actually made something that we could consider a product. All right, now this is not a particularly good diagram, this one. That leaves us, however, with another one of them. And of course, that can then go background to react with some more methane. And this is why this is propagation. It's a chain reaction. Now, we will get to a point where we start running out of stuff. And you've got some options that will terminate this whole process. The first option is, well, a termination step is actually shown here, where you could have methyl radicals bumping into chlorine radicals, because there's plenty of both of those about. They just make the chloromethane. That's it. That's essentially the end of that. But you could also have two methyl radicals bumping into each other, and that makes two methyls would make a, it's actually ethane. Now what's wrong with this particular diagram, apart from the fact we haven't got any curly arrows on it, is there's also another termination step possible. What could that be? What if we're left with, we could have methyl radical plus chlorine radical. We could have methyl radical plus methyl radical. We could also have no hydrogen, no, that's not reacting. We could have chlorine bumping into another chlorine, couldn't we? So, you know, if it's free radicals which are mopping up in the termination, what would we end up with? Well, one of them. And of course that could then go back to the beginning, be broken apart again. But it depends how much you've got. Now, one of the things that can add to your explanation when you're doing this, apart from curly arrows and stuff that I'm going to come on to in a minute, is this as far as it goes? If we were to just write an equation for this, because you'd be looking at this and thinking, if we start with methane and chlorine and just look at the simplest reaction that we've got here, one of the hydrogens has been replaced by a chlorine. We get that. Is that it? Not necessarily. Because if chlorine replaces one of the hydrogens on a methane, will it just stop at that? Why would it? So, you know, what we've done so far is that. Now, if you've got enough chlorine, it could go on and replace all the other hydrogens, basically. All right, you could keep feeding that back round and over and over and over. So ultimately, what you can get is this, where all the hydrogen has been replaced. So that would be tetrachloromethane. Carbon tetrachloride, they used to call it, which I think is dry cleaning fluid. But, you know, you can see that if you've got a chain reaction and you've got enough chlorine, then you could do that. Doesn't matter particularly how much methane you've got, does it? But you've got to have enough chlorine to keep that going, because the free radicals will just, they'll keep kicking out more and more free radicals, won't they? You see, you've got this chain reaction going on up here. So, yeah, but don't, you know, I'm not recommending that diagram. I found one that was a bit better. I don't want to find sort of the perfect diagram for you, because, you know, this is your assignment after all. But I found one, I was looking for one with plenty of curly arrows on it to describe what was happening. So a better approach, space, might be this. Okay, so what we've got with this one, this here represents ultraviolet light, basically. So that's energy. So here you can see good use of curly arrows all over the place. Possibly, you know, over the top a bit, maybe even. The first one here, the line between the two chlorines represents two dots. They're not there, they're not drawn there, but you know they could be. You know, could put them in there and there, and those single electrons are being given to the two chlorines on each side, like when I drew the homolytic fission thing. So that produces our two chlorine radicals. That's the initiation step. But the fish hooks there are like the ones that we had on the previous board, showing how you get the fission producing the two radicals. The second and third lines here, these are our propagation steps. So we've got our chlorine here with our this line. We've got our chlorine radical giving up its its unpaired electron. Well, not so much giving it up, but using it to join with a single electron from the bond between CH3 and that is a particular bond in the methane. All right, this is CH4 here. All right, that is CH4. It's just showing one particular bond where you've got two electrons there. One of them is being used to attach the hydrogen to the chlorine. So one of these electrons plus that one gives us that. That's rather odd because I would want to put a pair of electrons in there. Like I say, these are not what I would consider particularly good diagrams. They're sort of slightly mutant Lewis diagrams, I think. The other fishhook here, this one, is showing that the other electron that's holding that hydrogen onto the methane leaves that bond and is then attached to the methyl group there to produce this methyl radical. The other propagation step is that once you've got your methyl radical, then the unpaired electron there can effectively be responsible for splitting another chlorine molecule so that one chlorine atom, or a chlorine free radical if you like, is then attached to the methyl free radical to give us our product. That's our main product, and that's fine, you know, you'll pass if you produce that. The other one is left on the chlorine, so we end up with another chlorine free radical, so that goes then back to this one and goes in there again. And then this time we've got 3 termination steps. As I said with the other one, we were one missing. So we've got here 2 chlorine free radicals could bump into each other and reform a chlorine molecule. We could have 2 methyl free radicals bumping into each other and forming ethane. Or we could have a chlorine and a methyl free radical each bumping into each other and creating the chloromethane. And all of that is done on the back of single electron movement, so there's a lot of fish hooks in there. All right, like I say, given enough chlorine, you could go on and get rid of all the hydrogen out of that. Now, I don't want to do any more on that because, you know, it is perfectly easy to find on ChemGuide. The other one, electrophilic addition, isn't it? Electrophilic addition what we're looking at is ethene and yours is hydrogen bromide, isn't it? So I've got to use hydrogen chloride. Okay. And we end up with this. Chloroethane. Now, if we draw this out without any electron movement, something like that, the ethane starts life as, oh, it doesn't really help to draw those at an angle, I must say. It's a lot easier if I drew them straight up and down. And what we're going to end up with is, doesn't matter which way round I put the incoming on this. Strange. Okay, the board is just making a small attempt to be awkward. Right. So we start with a double bond in the middle there. That is that's got the pi bond, it's got these electrons above and below the plane of the molecule, which are ripe for attack. Right? So the important thing here is going to be the orientation of the molecules when you start. So you've got the methane and chlorine in your handout, with a full explanation in there as well. There's loads on it. Giving you far more than I should have done. Right, yeah, the electrophilic addition. I think I haven't given you quite so much on this. But maybe I have. Yeah, probably have. I think. Oh, there's no point in pretending, actually. The example that Jim Clark uses, and remember, when you reference, that's Clark, comma, year in your work, and then Clark, comma, J dot year, not Chem Guide. And no Jim. The thing about the hydrogen chloride molecule, which I haven't drawn in here, is it's very polar. There's, oh, that's not a word we've been using in this, but there's a big charge separation. So which end's going to be positive? The hydrogen, yeah. So we have that, whew, that's a strangely shaped delta, and that. Now, the bond that's going to be attacked, I'm just going to do this fairly roughly, I think, rather than give too much away. We've got the sigma bond between carbons like that, and we've then got the pi bond like that. Right, that's our hydrogen chloride. This is our ethene, C2H4. Sorry, lost it for a minute. If the pi bond is lots of electron density, which end of the HCl is going to approach it? The H or the Cl? You've got a 50-50 chance, come on. If this is negative, what's it going to attract? Positive, yeah, which is the hydrogen, yeah. So, the hydrogen, I do loads and loads of diagrams to sort of make this work. What you have happening, I was trying to do this without giving too much away, is really hard. You end up with the electron sort of density being increased. If it's approaching like that, do you see how that happens? The electrons in the pi bond here, all right, here's our electrons. Here's the slightly, I haven't got room for a delta, so I'm just going to put a positive there and a negative there. The electrons will be pulled towards the hydrogen. Does that make sense? The hydrogen is the electrophile, really. Yeah? So it's going to pull the electrons away from the pi bond. And as that happens, the electrons in the bond here are actually repelled towards the chlorine. Right? Oh, electrons, aren't they?
No, the one that pulls close to the hydrogen. No,
These electrons being pulled towards the hydrogen will tend to push those electrons towards the chlorine. Yeah? So what we end up with from that, you then get a break here because the chlorine's been pushed away. But we get a rather strange thing. How do I describe this? We get, and I'm doing this I'm trying not to use any curly arrows, in case you hadn't noticed, because I want you to be doing that. I can't give all of this away, can I? You end up with that hydrogen ends up stuck on there, right, on that side. You then get, you've got two hydrogens over here. The chlorine is now, it is actually a proper chloride ion. But if this has lost an electron in forming that, what we end up with is a positive charge over here. Because what the electrons in this bond got used to join that hydrogen on over, yeah, it doesn't matter which one it is, let's say that one. Now, if you've used up some electrons, you're left with a positive charge. If you've taken the electrons away, you take away negative things, you're left with a positive thing. Now, this whole, well, it's this end really, has a rather strange name, and I'm just trying to find where you can find it. Ah, there it is. I think it's probably the last sheet then of what you've got. Important term. There's a little box. Is it on your very last sheet? Very final sheet in the handouts. Yeah? Up at the top there, important term. We tend not to call it a carbonium ion anymore. So we call it a... When you look at that, how do you want to say it? No, we don't use carbonium anymore. The other word, how do you want to say it? Sorry? There's no X in it. No X in it. When I look at that, I want to say carbocation. It's not. It's a carbocation. Yeah? You know, cation is a positive ion. So this positively charged thing with a there, that's a carbocation. But I always look at that and I think, carbocation? It's a bit easier. Yeah. Not surprisingly, this negative ion here will react with that, and this is where, all right, this is your chloride ion. That. I've got a lot of dots and things around on these diagrams that are not really very helpful. It's a bit like this plus and minus here are misleading. They really should be delta plus and delta minus, because particularly that one on the chlorine makes it look the same as the chloride ion, and it isn't. All right, that is a delta minus there. It means it's just slightly negative, and then once it gets that pair of electrons, it then becomes a chloride ion. So what we're then doing at the end is reacting together a carbocation and a chloride ion, and then surprise, surprise, that's where we end up with our So this is chloroethane. All right, and that's doing it without any movement of electrons. But there are plenty of them about, plenty of diagrams that will show you what's moving where. If I was to go back and put them in just to be a little bit kind, I haven't really got room, but I've showed partially. I mean, that's really that's movement of a pair of electrons there. Then those move to there. All right. Let me just get rid of something that's misleading, and that's a little dot there. So there we've got the electrons being pulled towards the hydrogen. That is movement of a pair of electrons. The other one's being repelled towards the chlorine. That's movement of a pair of electrons. We then have we'd have the electron pair here actually going into that space and creating that bond that we've got at the end there. I think I've given enough bits away. I think with that and Chem Guide, I think you've got more than enough to finish that off now, really. Okay, the assignment's due in 2 weeks' time, so you've still got plenty of time to sort of get your heads around it. And I will allow a bit of time, I mean, you can ask me questions if you need to next week on it, probably. And then next Monday's chemistry, we're going to, let's say, make a start on the big unit. So don't forget any of this stuff, but you won't need it on a daily basis necessarily. You don't need to be carting all the stuff back and forth with you. I mean, things like a periodic table is always useful, although we've got one on board, I suppose. But yeah, we will have a different set of handouts, and I will do the handouts in 3 packs, one for each learning outcome. It just, it's a bit easier. I can keep on top of it a bit better. All right, I'm not going to do anything else now because I've run out of content, really, and any more would be basically me standing here dictating the assignment to you, which I think is probably not very professional. So we will, we'll leave it at that in terms of content for this unit. And if you want to stay here and work on it now, you can do. I'm going to be about for a while at least until I can't breathe properly. And if you want to go off and work on it on your own, that's fine. And yeah, other than that, I will see you. Well, I shall actually be around tomorrow morning because I don't have to go to Yarmouth now. But I shall see you tomorrow afternoon for biology anyway, and I can't remember what we're doing with that heart, I think. All right, so we will stop at that point.